So lab tomorrow, quiz Monday.
Wow.
And what's cool about today is I've kind of already taught you it.
Nice. So we just don't need to do this lesson.
No, we're gonna do it. Just because it's not the easiest thing in the world. So the reason why I say I taught you before is because I kind of began talking about it when we were doing, it's polarity and it's showing the partial charges. And the only thing new is putting in dipole moment, but it's still along the same lines of the polarity stuff that we've been dealing with. Okay, as you guys know, covalently bonded substances do what with their electrons? Share. Okay? Right? We're all good on that at this point, I'm hoping. Correct? Okay? Now we've talked about there are two ways that they share. What are those two ways? They either share them equally or they don't share them equally.
Polar.
Was that hard? Did I not word that question right?
That was a little bit weird wording, yeah.
Okay. And what do we call a covalent bond where the electrons are shared equally?
Non-polar.
Nonpolar. And what do we call when they share not equally? Polar covalent. Okay? So, when we have the two, sorry, what is the situation where we have nonpolar? What typically is bonding?
Same number. Same as carbon and carbon.
Same element, not necessarily just the same number of valence electrons. Because if I have fluorine and chlorine bonded, okay? So they have to have the same electronegativities for them to be nonpolar. Okay? For it to be polar, what creates the polarity?
Differing electronegativities.
Differing electronegativities. Yes? You with me, Brevin? What?
Yes.
Okay? So what ends up happening here is we have guys with two different electronegativity values, and what really is electronegativity in a nutshell? When what? Pull on electrons when?
The lustful desire of electrons.
The lustful desire of electrons.
That's something I can relate to. There we go.
Yeah.
Wait, did that just get?
I'm gonna show your dad.
Oh! Okay.
All right.
Would you look at that?
All right. Now, this is also something we've talked about. Okay? We've talked about how the greater the difference in electronegativity, the more polar it is. Right? We have talked about this. What is the type of bond that we say has really large polarity?
Ionic.
What was that? Did you say big polarity bond? When have I ever said that? Okay. So, and we talked. Have we also talked about really how there's no such thing as an ionic bond?
Yes.
Okay, it's really just an extremely polar bond.
Oh.
Easy.
Okay.
Okay.
However, we do say that if the electronegativity difference is great enough, we give it a new name and we call it ionic.
Yay.
So, let's say, actually, let's do that. Let's go dipole moment.
Dude, chips is in. Ooh.
Right, so let's say hydrogen
Chips in.
is bonded with chlorine.
Rude.
Okay, so what we're going to be doing today is we need to be able to show where the pole of electrons is going, what the partial charges are, and put a dipole moment in. Okay? So, if you're struggling at all figuring out how to do polarity, you might want to pay attention. Okay? Essentially, what you're looking for is what, Gage?
You're looking for electronegativity.
Oh, that's kind of right, actually.
Or how close they are to the octet. How close they are to become stable.
Yeah.
Is that close? I I have no idea what you're talking about.
Yeah, sit up.
I forget what I was thinking of.
He was like, I was
Hammocks?
Okay, so when you're trying to figure out polarity, trying to figure out how polar something is, you're really going to look at electronegativity. That's the very first thing you should be thinking about. Okay? So which element up here is the more electronegative element? Chlorine. Which means that these two shared electrons aren't going to be shared perfectly equally because they're not the same element. And which means that the electrons are going to be pulled more one way versus the other. And which way are they going to be pulled more towards? The one that has the greater pull. The one that has the greater electronegativity value. So with that being said, we can create polarity. What is polarity? Define it for me. Opposite regions of opposite charge is what polarity is. So let's identify what the opposite regions of opposite charge are. This side of the molecule
It's
has
negative.
a specific charge. It's going to be partially, can't see. I have yet to make one.
No.
Oh, yes!
That's
pretty cool. Why do you put it back in the basket?
It was partially.
Because I used to use those with like whiteboards, and I've used them sometimes.
Remember, it was partially.
Okay, so partially negative. That's a fresh
That's
marker.
now you have to do the whole thing.
No, I don't. Okay. No. So what ends up happening is the shift of electrons go that way. By default, what's the other side have to be then?
That's 5 cents. Hey, you can give that to me.
That's like 3 diapers.
What? Trevor, it's still on your desk. She put it back.
Where was it?
It was there, and then she was gonna throw it away. And then she's like, nah.
Okay. Now, here's dipole moment. What essentially a dipole moment is? It says the measure of the amount of polarity of an entire molecule. Yes, that is what it is. I'm going to break it down and make it a little bit simpler for us. It's going to show us the general direction of pull. Okay? So what a dipole moment is, it's a little, it looks like this. So I'm going to show the dipole moment of this, and I'm going to explain it in a second. So that's what the dipole moment looks like. The arrow points to the right. Why, do you think?
That's where the electrons are pulled.
Okay, that's where the electrons are being pulled. So your dipole moment is typically going to be pointed towards your more electronegative element. Now, this also might help. What does that look like?
A negative.
Positive.
An arrow. Oh, no, wait. That's a positive. Another negative. Draw this. Not bad. Draw this. You guys pull on the block. That's stupid. Or do it there.
I don't really want to.
Dude.
Or pulling the boats.
Okay? So, what we're going to be doing is we need to identify where the direction of electron pull is going to be. Now, you should also note that the bigger the difference in electronegativity, the stronger these charges are. Does that make sense? If this were fluorine, these charges would be stronger. Okay? Therefore, there would be more of an attraction to the neighboring molecules if it's a stronger partial charge. Now, let's do a couple more of these guys. I'm going to ask you this. If I have a molecule and it has different elements, does it always mean it's going to be a polar molecule?
No.
Why not?
Because.
Okay? So let me show
Usually
you.
when people ask questions that say always, they're
It's
usually a
no.
false.
Everything is
Jesus, always loving. Yes. Yeah.
Oh.
We always like what Jesus does. I said not always. I don't know what you're saying.
Did you sleeping?
That's not
No,
always.
he just woke up exactly when you spoke.
I woke up at 2 a.m. this morning.
Alright, you ready? Good for you,
I
Trinity.
don't drink no
How
juice.
minutes did you already go early?
Okay, can we finish, please?
Yes. That does not have polarity.
First of all, that is a beautiful
That is
structure.
beautiful.
That is good. That's
great.
very clean.
Yeah, it
The
is.
bottom CL's a little bit lacking.
Yeah.
Gage, shut.
I think it's
Shut up.
beautiful, so.
Yeah. So, hey, we look at this guy. Every single bond there is a polar bond.
Spots.
Okay? So, now, I do not want you to do this, but I'm going to use this to kind of show you the direction of pull. Chlorine's more electronegative than carbon,
Yep.
so it'll be pulled that way. However, dipole moment is specifically for the whole molecule. So don't write this. I'm just showing you direction of pull. I think I ruined it.
Yep. Yeah.
Wait, so that bar needs to go on the, that
Yeah,
line needs to go on
and
the
the L on
other
the C
side.
on the bottom
He's
is
going
not
on
If you
the
want it to
same
be
height,
beautiful,
so
that
it
would
could
be
be
put
considered
it on the other side.
Oh, I have good hills.
Hey, you said it was beautiful. Yeah.
You know what? Sometimes beautiful things change.
That's
What?
beauty.
Yeah.
Never your wife.
Nope, they still change.
Never your wife. They're always
Okay,
beautiful.
Brevin, you're so awkward. What are
Making
you
the
working
arrows
on?
filled in was a bad decision.
Stop, Trinity.
Yeah, it is,
It's
because
not
then you can
nice.
see how different they are.
Oh, and now that
Why is it so small?
You didn't fill them in.
Why is it so hard?
It kind of looks like chlorine, the bottom chlorine.
You're not even-
Looks like an activity, I feel like.
Yeah, they're like, some of them's like really short.
I feel like you don't ever get anything out of my part.
Probably not.
I do, actually.
Look at our text
Really,
grades.
I'm
We're
an
so
awful
smart because-
teacher. Just say
Wow.
it. Say it right
Hey,
now.
you were the one
Uh,
who said you wanted it to be beautiful.
You were the
so-
best teacher.
Did you-
Ah!
Mr.
Okay.
Kramer,
What?
I learned this. This is bad chemistry. This chemist, okay?
Like oxygen and potassium?
No, he was a chemist. Like this guy.
A chemist?
This guy loved
Like
coffee
dog.
and he was a chemist, so he came up with this. I used it this morning. It's called the Chemex.
Okay.
It's like, and it's well-known coffee maker. Never heard of it.
Okay.
And it uses chemistry in the filtering of the coffee to take the toxicity
Toxins.
out of the coffee to make it smoother.
Yeah, but it doesn't help you stay awake.
It does.
It still has caffeine.
Depends on what you define as the
Yeah,
toxic part of the coffee.
Still full.
Interesting. It's just a smart filter.
Yeah, it was a chemist. It was a chemist that made it. You know?
Yeah. So essentially, probably what they're doing is taking a filter and having it being like have a certain polarity to it. To be honest. And so what ends up happening is, I'm serious. What probably ends up happening is certain molecules aren't able to go through because they're attracted to the charge that's in the filter. That's how a lot of filters work. To be honest with you. That's how
How do they make the filter charge?
How do they
It
make
was
this
taking out.
they have chemicals in there
They
that are
just put
charged.
it in some.
They have chemicals in your water.
So oil is attracted to what?
So that one you want that to be non-polar.
Oh, because it takes the oil
Yeah, so then the filter is not polar.
out of the coffee.
We'll talk about that when we get into the dissolving chapter. Like dissolves like, and so non-polar things don't dissolve in polar things.
Made
And
in
polar
the
things don't
USA.
dissolve in non-polar things. Anyways. Brevin, are you with us? Yeah, I need to be able to.
I'm doing 1, 2, and 3, and 4.
Yeah, we gotta be able to get through this, okay? What I'm trying to show you here is, there is a partial charge here. What is it?
Partial
Chlorine.
Negative.
Yeah.
Where's the partial charge here?
Partial
Negative.
negative.
How about
They're all
here?
partially negative.
How about here?
Negative.
Okay? So if they're all partially negative,
And they all.
how do we not have polarity? There's charges there.
They're all
all equally
equal.
distributed
They're all, yes, exactly.
Throughout
So
the.
that
answer.
is most likely going to be a gas.
Yeah.
Oh.
Yeah. Now, you guys didn't give the right answer, actually.
Natalie did.
What did Natalie say?
I said they're all.
That's not the right answer.
That is, I think it is.
They are pulling equally, but that's not why this doesn't have polarity.
They're all the same charge.
Yes.
Oh, Trinity.
They are not opposite charges, are they? Don't you need to have opposite? Yes, that's opposite regions, but they're not opposite charges. So we do not have polarity. Polarity is not opposite regions of the same charge. Okay? And yes, there is a positive charge, but it's right in the middle. And so how are you going to get that to be attracted to some neighboring molecule if it's sitting in the middle?
No.
You're not going to.
So it's a gas.
Okay? So now, here's what you can do to determine quickly whether it's polar or not. It's called the symmetrical test. I think I
Yeah.
briefly talked about it. And, man, I feel like I just don't have to teach this anymore.
Okay, so why do they say that, you know, like perpetual, what is it called, perpetual motion or whatever?
Okay.
There's nothing that's 100% will go on forever, you know? Like in perpetual motion.
I don't know. That seems like
Like,
completely different.
scientists have taken so much time on making like a machine that will like, let's say like sway forever without any use of energy.
Well, how in the world are they going to do that? They have to do it they have to remove so many environmental things. Like you have to be in a vacuum. You have to have like the perfect oil.
Yeah, they do it with magnets. They say magnets wear out over time, and all that.
Entropy.
Why don't they use
Entropy. That's why.
the charge of electrons? Like,
But if
The
they want to do
energy
it without
in
energy,
electrons.
if they want to do it without energy, that's kind of defeating the purpose.
no,
No.
no. Like a gas. Does gas eventually run out of energy? Those electrons moving everywhere, or do they just have
It depends. It depends on.
unlimited energy?
So when gas particles are flying around, yes, they generally maintain most of their energy because the only way they're going to lose their energy is if they collide into something. And if they collide into something, they can transfer some of their energy to whatever they're colliding into. But if they don't ever run into anything, they're going to maintain Newton's first law: an object in motion will stay in motion. The reason why gas molecules don't slow down is because there's no friction between, they're not coming into contact with something.
So what they need to do is put gas into a vacuum, then have something that will run into the electrons that somehow creates energy,
But it doesn't
and the
gas
electrons
have no-
go
Well,
back.
first of all, you can't create energy.
But could you make something that has everlasting energy?
No.
I don't think so, because
The Bible talks
like
about
like you said, magnets things eventually wear out. That's just the second law of thermodynamics, essentially.
Well, you could make a very
Yes, probably.
What is it? What's the transfer of energy called?
It depends on what form it is in.
Yeah, like this.
Anyways, let's get back on this here.
Wait,
Alright.
so if everything's losing energy, then why do people say that there's gonna be heat death? Wouldn't that be more energy?
I've never heard of that.
Like a heat death in the universe?
Heat death? Heat death?
Like global warming?
Global warming?
No, like
What are you
the-
talking
Global
about?
warming. Like, if
Like
global
going-
warming were to happen, it would be getting more energy, because you need more energy to get hotter.
The only reason that people are talking about global warming is because
The sun.
the sun isn't changing. It's our atmosphere's ability to block out a lot of the bad, harmful energy. And so when our atmosphere can't do that, more energy is going to come into our planet and heat it up. And
It is.
Well,
that's essentially the
sun is.
idea.
Well, it's not really. The sun is dying out.
Yes, it is. Did you just hear what he said?
It changes over time. It's not
Like,
then
it's
getting
like
more
stars.
energy.
Entropy.
Alright, anyways.
This fall it was a lot colder than it was last fall, so.
Guys, no more rabbit trails. I see exactly what you're doing.
No, I'm actually.
No more rabbit trails. We are done.
The sun is dying out. Though.
Shush.
Yeah.
So then why would
No,
it be
it's
getting hotter?
not polar.
Did you not hear Kramer's explanation?
Ah.
Polar.
I gotta be careful here.
What's the atmosphere?
I don't.
I gotta be careful here. So actually, here,
Actually,
pay attention. You're gonna want to pay attention to this, I promise. Don't you think that how we write the shape of this guy is gonna determine whether it's polar or not?
Yes.
Ah, it is. So, in order to determine whether it's going to have polarity or if it's going to have a dipole moment, it's going to be based upon knowing what its shape is going to be. So,
Oh, shoot.
we have to look up here to see, is this shape correct or is this shape correct? Because if this shape is correct, it has polarity. If this shape is correct, it doesn't have polarity. So how do we know
Well,
which is the correct
there's
shape?
two regions, two bond regions. So it's linear.
Two regions, both those regions are bonded, it's going to be what?
Linear.
Linear. Okay, so this isn't going to have a dipole moment or polarity because I could cut it in half this way, and I could cut it in half this way, and it would be mirror image. Okay, I said that earlier, but I'm going to refresh it. It's going to be not quick way to tell if it's a non-polar or polar is the symmetrical test. If you can cut it down the middle and horizontal, and it's a mirror image both ways, non-polar. Okay.
Oh, this one's different.
Okay, now this next one, again, depending on how we write it, is going to determine whether or not it has polarity. So the question is it a bent structure or is it linear? It's bent what?
109.5.
Okay, so we know it's not this because there's 4 regions, 1, 2, 3, 4. 2 of those regions are bonded. That's going to be a bent structure, which means it is going to have polarity because if I do the symmetrical test, it's not symmetrical. We got to figure out where the dipole moment is going to go then. Where is the negative side of this particular molecule going to be? The sulfur is more electronegative, so you have electrons being pulled that direction. So I would do this.
Cute. Oh, it's a bow and arrow. That's so cute, man.
It's actually just an arrow, not a bow.
Nope, the SH.
Well, there's no string, so.
Well,
It's actually just not a word in there, bro.
Alright, I want you guys to do the last two. I'm doing too much work for you. That's why you guys are on rabbit trails. Do it!
like,
Sit up, Gage.
I like it.
And then there's Quinlan, who is way on top of things. Has got it all done. She's the perfect student.
It is all wrong.
All wrong?
For number 4, well, how would you draw the arrow?
Who's right?
Draw 2 arrows?
Yeah, that's right.
Would we draw 2 arrows?
No, you would just draw the 1 arrow. It's kind of hard. I wouldn't draw this one through it. But guys, probably most of the time, when you're drawing it, try not to draw it. I should have drawn it through it. I should have probably just done like that. Because sometimes you can't draw it through without messing up what it looks like. Okay? You, Marty, you done?
I'm thinking here. I'm trying to.
Yes, Tanner?
Bring it over.
Okay?
Now what?
Draw this.
Yeah? Well, you're trying to figure out what's the more electronegative, guys.
what is a pyramidal fruit look like?
Okay. Since they're pulling in opposite directions, the next question you should ask is symmetrical or not? Does it follow the symmetrical test? If you were to cut it, first of all, you didn't even write that correctly.
I just did this, so that's.
Carbon and oxygen are both not stable.
No, you said.
How many electrons are around carbon?
Because since the one's in the side, I
I'm talking about right now, as you've written it. How many electrons are around carbon?
But I don't
6.
exactly.
Is that stable?
No, so I need to do.
I know, I was like.
So, but where's the second region? There's one.
I just did this symmetrical. It's the only reason I did this.
How are you forming a bond between oxygen?
But I don't know why.
Where?
Well, you know it's polar because.
It's on the board.
Because,
Yeah, I know, but.
No matter how you do it, it's like.
but I don't know, since those two, I
I
don't
know,
know which way
those
to
two are
draw
like,
the
that's
arrow.
making you
Yeah.
really.
The problem is you shouldn't be using your pen. Because,
No matter what.
right, that's essentially just what you do here.
And make
You're
this
still missing your 2 electrons. Stay. I want to show everybody else this quickly. So this guy looks like this. Which one's more electronegative? So your dipole moment will look like that. Okay? This one. This is probably one we should spend a little bit of time talking about. Okay? These two pull equal and opposite, so you're not going to have any polarity that direction. However, you have a pull this direction.
Good job, Quinn.
It should look like that. Yeah.
1, 2, 3, 4. 4.
Yeah, well, that's how you have it is not stable, but you still have more work to do. You have all the electrons where they need to be at this point, but I still have a bonding site here and a bonding site here. And I have 2 bonding sites here. Anytime you have unpaired electrons, you're probably going to need to form another bond. You never want to have electrons.
You will.
Well, they're for a speech class, and then I'm giving the rest to my father. So,
One Oreo ball.
it probably will.
And your dad literally told our class, he's like, go ask out for Oreo balls.
No, I'm gonna make.
Yeah, he told the foreign exchange students to do that.
I know. The only way to get 8
It's okay, I could come back then. No problem. No.
Don't you speak Latvian?
I do, but I'm a foreign exchange
You're
student.
never going to have unpaired electrons.
I don't know.
I have 1 red carbon.
Oh, Marty.
And the other in the unpaired electron
Shot.
How many did it have?
Oh, dang it.
How many did it have here? 2, 4, 6, 7. I still have 1 unpaired electron here. And I have 1 unpaired electron here. Now do you see how that other bond is kind of stable? Now how many electrons do I have around first? I just get stable. Does that make sense? You should never have unpaired electrons. If you have unpaired electrons, you're missing bonds. Does that make sense? Okay? And the symmetrical test will tell you if it's polar or non-polar. I cut it in half this way, you know what a mirror image is, right? It's the same thing on both sides. And I cut it this way, mirror image on both sides. It's not polar, you don't have to put a dipole moment.
Tell them something about their buttons.
But something like this, if I cut this down the middle, is it a mirror image?
I'm not doing anything.
No, so it has to be polar, which means I'm going to have to put a dipole moment. In that case, we're looking for electronegativity. So it's more electronegative, the chlorine. So then I point it towards being pulled by the chlorine. Does that make sense? Q2! Plutonic directed
Your arm was up.
affection.
Directed.
Okay, I'm still slightly. I'm still slightly bitter about how you guys did.
I shot Lauren.
That's not even. I got rid of my
to be
nonsense.
fair,
I got rid of my.
I'm not mad at you.
To be fair.
You should never have to do that though. You should
I
be able to
said
play
No,
normally.
they wouldn't have been able to.
That's what I'm
Exactly.
saying.
But we also didn't play.
This
We
is
didn't play that right because if they all come back, only person who could have seen me is him. Yeah, that's what I said.
I mean, we
I was like,
were
I'm not
coming
saying
there.
Wait, but actually though,
Well, we should have, but we should have.
because what I was
This
saying,
makes that a little
I
bit
took
better.
the
That
lane.
round was
I took the lane of neutrality. Because remember, I took
not
away
true.
your, I took away your
But you
Bible,
never did anything
but then I was
to her.
gonna bang her.
Because you couldn't.
But I couldn't, that was the problem.
Emma.
And so I was faced with the decision of discarding and then just banging. And if I would have waited like another 30 seconds,
Oh, you okay, lad?
longer and discarded it instead of banging it. But I was like, I'm a ghost, I have to win this, so I must have done it. You know, that's okay. But it's like, I'm still,
Dude, we just had the funniest conversation in college.
yeah.
Very much. Pretty tragic.
So